So we are at page 77. So just a brief review. Last week, we have talked about two things that are very important, fundamental and important. A little bit of review, right? One is the Neyman-Pearson approach. The Neyman-Pearson. So let me see. The Neyman-Pearson approach. So let's take a look at the 65, 65, 60, 65. Uh, the Neyman-Pearson approach is to say that we want to maximize PD for a given PFA. In other words, this PFA is false alarm, right? So by the name of false alarm, it's something no good. So what we want to do is we want to avoid that false alarm. false alarm 就是误警报，误警报，所以我们不喜欢，我们想要让它少一点。Then PD is something good, because it means that when the ground truth is H1, when the ground truth is H1, 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 we have a H1 detection. That is something good. So PD is something we like to have. PFA is something we like to avoid. So Neyman-Pearson criteria by itself is saying that we like to set a threshold on PFA. In other words, you should not make a decision that has a PFA higher than alpha. Then under that circumstances, we maximize PD. So as a result, after some mathematical derivations, then we will say that uh, we decide H1 if the likelihood ratio, this is the likelihood ratio, larger than gamma, and the likelihood ratio is the P of x condition on H1, P of x condition on H0. And then the threshold is found from false alarm probability equal to alpha. So you have to integrate this likelihood ratio, the region for this likelihood ratio larger than gamma. How come? Because under these circumstances, what you are doing is you make a decision for H1, while in fact it's H0. So that's probability of false alarm. Then you make a decision for alpha, and that's your PFA. Okay, and then we have a example. The example. Assume that we require PFA equal to 10 to the minus 3. Then we decide H1 if this is larger than gamma, which follows from this likelihood ratio formula. So you have this derivation. Then of course, as I said, you have a lot of things to simplify. 1 over 2 pi, 1 over square root 2 pi, those things cancel out. Exponent, when something is exponent, then the exponent of the exponent can subtract each other. So it goes this. Then finally, you have this, something like this. Okay. Okay, then we go to page 66. Then you have this determine gamma, you want to determine gamma, so PFA equal to something like this. Then with some numerical approaches, just because it's not easy to calculate those Q functions and exponent functions. So you make a change of variable, gamma exponent beta, so on and so forth. Then you get something like that. You get something like that. You get something like that. And then PFA is equal to this, and so you want to integrate this to this. So let me just be going a little bit slower. This thing is something like is actually this. Okay. Page. We can go back to this Neyman Pearson approach 65. We have a PFA equal to something. Then you have PFA equal to something. And then uh, of course if we decide that x0 is larger than 3, then uh, x is larger than 3, then it satisfies this. So now the question is, you may be wondering, how come we know x larger than 3 will contribute to PFA equal to this? This is not coincidence. Okay, gamma prime equal to 3. This thing corresponds to 10 to the minus 3. This correspondence is not coincidence. It is what? It is by calculation and numerical approaches. As I say, it's not trivial, but somehow people can use numerical approach to do that, to solve that, so you get this gamma prime. It's just a coincidence. Usually, the threshold won't be that uh, won't be that good. Won't be that good. Just like 3. It will be something like 3.25, 3.356, something like that. It won't be just like an integer. Okay, this is just a coincidence, right? So I'm trying to emphasize that this 3 is not the 3 here. It's not. Okay, it's coincidence. Okay. Okay, so let's come back. Gamma prime equal to 3. Then you can calculate your PD, Then the PD is like this. PD equal to something like this. And condition on H1 is sample larger than 3, right? How come? Because when this happens, you are going to make a decision for H1. Condition H1. This is exactly what a detection is doing, right? This is exactly a detection. So we are doing a detection, a probability of detection, and you integrate 3 to infinity, right? So you get something like that. You get something like that. Then there's for example, if PFA is 0.5, then the threshold is found from here, as gamma prime is 0. As gamma prime is 0. This is a little bit more trivial. If we look at this distribution, it's a Gaussian distribution with 0 mean. So what happens is, if it's 0 mean, then it will be symmetric. For a symmetric distribution, you want to have a 0.5. You set a threshold at the middle of the distribution, which is 0. So this is more trivial, right? You think the way I think, then you get 0.5 corresponds to 0 without calculations. Okay, then PD is equal to this thing to infinity. Of course, then this has a 1 here, which is not zero mean, right? Then let's see what happens. Then you start to calculate. You see, it's not that trivial anymore. It becomes a Q function of this point A4. All right. And then we also have another example like this. I'm going through quickly because this is just a review. And one important thing is the receiver operating curve. I'm going to talk about this. Let's see. The receiver operating curve. So we are at page 74. Receiver operating curve is to say that you have a PFA, then you have a PD, but they are all functions of something, and that something relates to each other, right? You have sigma square, you have number of samples, and you have gamma prime, which is the threshold, and also you have this A. In some examples, you have a signal strength or SNR in your equation. So you have a PD as a function of PFA. So that is something good, right? That is good. How come it's good? Because we like to know the relationship. Remember this phrase. We like to know the relationship between PD and PFA. So we like to draw a figure that represents PD versus PFA. That's the point. That is the point. Once you draw that figure, then you will clarify a lot of things. You clarify how this detector performs under different level of PFA. So that is aside from the threshold we talk about. This receiver operating curve is more general. It's a more general description of a detector because it gives you an overview of PD versus PFA. So let's come back to this 75, page 75. You see PD. You see this PD versus PFA. So that's receiver operating characteristics. So as you can see, the probability of false alarm PFA is at the horizontal axis. The PD probability of detection is at the vertical axis. And you, uh, as we all know, there are some properties. What property? If you have a probability of detection, the best thing you can do is you go to 1, right? 几率的最大值就是1，所以它不可能大于1。For the same reason, the maximum value for PFA is also 1. It doesn't go over 1 because it's a probability, right? It's a probability. Okay, and there are other properties. For example, if you have a uh, random guess, this is a binary problem. If it's a binary problem, then you have a random guess, then what do you get? 就是如果是一个 binary 的问题，然后你就随便乱猜，你不要用任何的 detection 的方法，那你就得到这条线，这条。This curve is for random guess. It doesn't make any meaningful detection. It doesn't take advantage of the information. Then you automatically get this. How come? Because you are making uh, half of your decision is correct, half is incorrect. So it's something like this. Is that just and then The other thing is if your gamma prime increases, then it goes to this point. This point is more of a conservative point. Why should I say conservative? Think about it. You increase your alpha, so it becomes very hard for you to make a decision for PD for H1. At the same time, it also reduces the probability of false alarm, right? Because it's hard for you to make a decision for H1. And the other thing is, if you make gamma prime to the minus infinity, it's very easy for you to make a decision for H1, and then vice versa. Your PD is very high because for each H1 instance, you make a decision for H1, so you are making good PD. At the same time, very very bad PF, which means you have PF equal to 1. Approach is 1. That is not good. And usually we like this to be to be going through this direction. For example, if you have a if uh, you have a detector that looks like this, then we consider it very good because it has, you see, it has a very low PDFA and yet very high PD. That's something good. And a perfect detector will be something like will be something like this. It goes all the way up to PD equal to 1 and then like this. That is very good. Okay, so that is the sort of the ROC. Remember, ROC is very important because it's very fundamental in this type of problem. And as you can see in many papers, I believe you see that also. Okay, so the next thing is we're going to talk about the Bayesian approach. The Bayesian approach. The Bayesian approach uh, is it has a prior information. So in other words, uh, previously in Neyman Pearson in our previous discussion, remember that we have not talked about probability of H0 been happening. We have not talked about H1 been happening, right? We just say that when we receive data, how should we do? How should we make a decision? Things like that. But we have not talked about the so-called inherent probability. So what's inherent? Inherent or prior means that the the probability that exists for those hypotheses before any observations are made, before any observations，就是你在做观察之前，那我们刚才探讨的都是观察之后的事情，对不对？观察之后怎么做计算，怎么算 R 伽马，怎么做四个 gamma prime 等等的。但是我们从来没有讨论到一件事，就是 H0 跟 H1到底它的内在的几率是多少，也就是这里我们称为 prior probability 的这个部分。那事实上它有没有可能存在？它有可能存在。但是先前不讨论，通常的内在的假设是它等于1/2啊，就是我们不假设不讨论，意思就是一半一半啊。好，那我先前曾经举例说，如果你今天在沙漠里面，然后我问你有没有下雨，这是一个 binary 的问题嘛，哈，有下雨或没下雨，那你可能会觉得说，如果就算我们没有做任何的观察，我也会猜没下雨，因为一年365天沙漠下雨的几率本来就很低。So in the desert, the probability of raining is very low. So if you don't have any observations, what are you going to do? You are you are going to say it's not raining, right? It's not raining because even if you are not making any observations, when you say it's not raining, you are 95% correct.你就说你不要做任何的事情，都不要观察，也不要计算，你就说没下雨，你大概95%还是会对，because the prior you have prior information. You know, in the desert, the probability of not raining is around 95 or even higher than 95. So uh, it's very important that you understand the prior, the concept of prior. 就是你在解决任何问题之前，我就是提醒大家，你在念 paper 或你自己在做你的研究，不管是哪个领域的研究，我相信你都必须要思考这个问题。你在做任何的决定、侦测、演算法之前，你先想一下 prior。如果你想清楚 prior 了，那你在做那个问题的时候，你的 formulation，你的决定会比较正确。为什么？一个重点是 prior information is like free lunch，就是免费的午餐。如果你有 prior information，你不用，其实你会浪费你的资讯，你很可惜，这是很可惜的。好，如果你没有学一门课叫资讯理论的话，prior information 是资讯理论里面讲那个资讯很重要的一块，很重要的一块哦。如果你不用，你是在浪费，而且甚至有时候你做很多的演算法，你的效能会很差，原因就是因为你没有用 prior information. If you have very strong prior information, you don't use it, you are wasting the information. Okay, so I just clarify the concept here. 我们先暂停一下，然后这是第一个筛选，然后接下来我们再进入下一个筛选。